In 2010, an unconventional paper from string theorists made headlines. Erik Verlinde proposed that gravity is an emergent phenomenon that could be understood as an entropic force caused by the changes in the information associated with the positions of material bodies. An entropic force, which does not require a force field, is an effective macroscopic force that originates in a system with many degrees of freedom by the statistical tendency to increase its entropy. Verlinde derives Newton's law of gravity from classical statistical mechanics applying the holographic principle, that is, that the description of a volume of space can be entirely encoded on a lower dimensional boundary to that region. This boundary is not accessible to us living in the volume, it's another description of the volume itself. He starts with a closed spherical boundary surface with n number of used bits of binary information encoded on the boundary. This information of the volume is evenly distributed over the area, and the number of bits is proportional to it. Now he wants to find the origin of the entropic force, so he needs to know where the temperature comes from. If the total energy is divided into bits, the statistical equipartition rule relates the energy to the n number of degrees of freedom and the temperature. Then with E equals mc squared and massaging all these equations, he reaches Newton's laws of gravity, by which masses move in the volume, maximizing the entropy in the boundary. He also derives Newton's second law of inertia as another entropic force from the change of entropy associated with information on the boundary and under radiation associated with acceleration. Verlinde's claim that gravity is derived from first principles is not exempt of assumptions, the main one being evidently the holographic scenario. This goes back to Bekenstein's idea of the entropy of a black hole. Another assumption is that only a finite number of degrees of freedom are associated with a given spatial volume, relating every bit of information to the existence of a blank area. Verlinde later argued in 2016 that his approach could give rise to a modification of the Newtonian laws similar to that required to explain galaxy rotation curves without dark matter, which is Milgrom's Modified Newtonian Dynamics. We explained MOND in our previous video, so check it out if you want to find out how it works. I won't explain it here again. He also claimed that dark energy could be derived, but I will focus on dark matter here. Notice how Verlinde directly compares his result with that of MOND instead of providing tests of his equations in real galaxy rotation curves to prove that such a modification really removes the need for dark matter in galaxies. This should tell you how strong MOND is in addressing the problem of dark matter in galaxies. One of the key differences with MOND is that the interpolating function of Verlinde contains the radial derivative of the Newtonian gravitational acceleration. It is also not clear whether if it has an external field effect, something quantized inertia doesn't have, and I forgot to mention it in my previous video about it. The external field effect is considered crucial in MOND in order to fit observations. And what was the response from the MOND community? There is an answer from Milgrom himself and Robert Sanders, in which they state that Verlinde's dark matter explanation is, and I quote, a formula of rather limited applicability and with no road to generalization in sight for the effective gravitational field of a spherical isolated static baryonic system. It cannot be used to calculate the gravitational field inside or near these galaxies with the rich MOND phenomenology. Notably, it cannot predict the rotation curves except asymptotically. It does not apply to the few or many body problem. It cannot be applied to the internal dynamics of a system embedded in external field effect, where MOND predicts important consequences.
You derive Milgrom's acceleration as equaling a sixth of the Hubble constant. So, as far as I know, you're the only person who's done that from first principles. I could be incorrect. Are you aware of any other approaches that get that same result?
No, but I have to say that of course I was aware of the work by Milgrom. I have this idea of how to connect it to the ideas of emergent gravity, and I wanted to see if that could work in also explaining the actual phenomena that we are observing. And I wrote down what I would call also an effective description.
But most remarkably, they state that the way Verlinde arrives to the MOND's introduced constant, the acceleration scale constant A0, is not a consequence of established principles or theories, but it is due to the freedom of choosing numerical factors along his derivation. There is also this study from Benoit Famey and others which claim that emergent gravity's modification a la MOND is inconsistent with solar system constraints due to its interpolating function, which was directly given by Verlinde. And another big name in the MOND discussions, Stacy McCock, also pointed out that emergent gravity is different from MOND when you have an extended mass and not the idealized point mass case, and that the data from galaxy rotation curves is challenging for Verlinde's model. So no, I don't think either that Verlinde has derived the acceleration scale constant. There are several candidates for A0, such as the size of a cosmic render horizon, a property of the vacuum related to the cosmological constant, the relative acceleration of most of the matter in the observable universe due to cosmic expansion, or the inverse squared mass contributions of the large scale. But as Milgram and Sanders say in their paper, these problems of emergent gravity are only there to stress that much more work is needed to be done in this line of research.
I think our theoretical understanding has to be improved. And I like to eventually motivate my colleagues also who are thinking about gravity and the way it's emerging from a more microscopic quantum description in terms of, well, entanglement or complexity and so on, to even think about those questions, because I think we have really a chance to verify our ideas in observational facts. And if that happens, of course, that would be spectacular. But I'm quite convinced, actually, at this moment, that this is going to be happening. And I hope it's going to be even generally kind of accepted in the next 10 or 15 years. Because I do think that our program of understanding gravity more fundamentally from quantum principles and quantum information is going to lead to these modified equations for the gravitational force. Anyway, we need to make a lot of progress in our theory to see how we can make that more precise.
We don't raise these problems to put an end to his idea, but to encourage further work on it because I think it's promising and at least it's a novel and original idea in theoretical physics. Thank you very much and see you next time here in Independent Physics.